Welcome back, everybody. Can everybody hear me well? So for those of you down in the corner there, it seems now that it's possible to actually move a little bit closer here, as the other folks have done, if you want to. Today we are going to start with a new topic, and this is the topic which is going to keep us busy for the next 2 to 3 weeks, and we are going to use this topic here about two body forces and many body forces to study the solar system a little bit later, and that's going to be the topic for the second midterm. And we are gradually going to bring in the different elements which are needed so that we can actually understand what is going on mathematically and physically. So today we are going to go through some technicalities, and we need these technicalities because these systems are actually systems which we can solve analytically, and that gives us invaluable insights about the systems which we are looking at. So we're going to start with the Earth-Sun system, and when we solve these equations, we can distinguish between circular motion, elliptical motion, parabolic motion, or hyperbolic motion. And all these are cases which we can retrace back to the type of potentials which we have. So the analytical aspect gives us invaluable insights about how the system will behave. And then clearly when we move to more than 2 planets, like when we go to the Earth and Jupiter and the Sun, then we have to resort to numerical simulations. But everything which we do now is going to gear up towards the second midterm. And hopefully, even if there are many small technicalities, you will see the wood for the trees. That's my hope. Today and also Wednesday are going to be days which are filled more with technicalities, but we need this in order to be able to analyze the equations. So I will try to step you through many of these details here. And I'm going to essentially to use the whiteboard. So the kind of overarching motivation for what we're going to do now is to be able to understand gravitational forces and what kind of motion we get or can expect. These potentials conserve energy. So many of the things which we have seen before, which we studied in homeworks, in different homeworks and the first midterm, they will appear again. So we're going to use energy conservation, conservation of linear momentum, angular momentum, all these things pop up. And we are going to look at internal forces only. So that means you're going to neglect any other type of forces. And with internal forces only, we are going to see that energy is going to be conserved here. And the gravitational force is one of these forces which allow us to also solve these problems analytically for 2 bodies, like the Earth, the Sun case. We're only going to look at the internal forces. There's no external force. We neglect friction or air resistance. And the thing is that the kind of arguments which we are setting up now, they are not going to be limited to a gravitational force only. So everything we do now will apply to a force which goes like the inverse distance between 2 objects to the power of something. And you will see that when you do the mathematics, these are going to be energy conserving forces. They're going to be forces which conserve linear momentum and orbital momentum. And these are things which we can test, both theoretically, by paper and pencil, and numerically, as you will see in the midterm. Any questions so far? So I'm going to switch pretty soon over to the whiteboard here, if that's okay. So the topic this week, we're going to deal with some technicalities. We need to define these problems. And the things which I'm going to go through today, actually parts of exercise 2 in the coming homework. So many of these technicalities are simply needed in order to move towards the analytical solution of a 2-body problem. And this is actually one of the few cases which we can solve analytically with potentials of this type. And you will see many elements of things which we have gone through. And we're going to prepare on Wednesday. Hopefully we get to the solution of the gravitational force problem in 2 dimensions. And if I get time, I'm going to use the harmonic oscillator in 2 dimensions as an example. And then Friday is again the homework day, and we just dedicate the time to homework number 7. So there are several things which we need to do now. And one is actually to rewrite the equations in terms of the degrees of freedom of the relative motion and the center of mass motion. We are going to make a transformation to polar or to spherical coordinates, depending on whether we are in 2 or 3 dimensions. And this gives us differential equations which are no longer coupled. This kind of trick is something you will see again when you do quantum mechanics and you get to meet the Coulomb interaction, which is used to describe the periodic system. You can actually solve that type of equation analytically as well, with a potential which goes like 1 over r, the relative distance between 2 objects. And you can do that if you switch to spherical coordinates. So this kind of trick, which we're going to see now, is one of these cases where you can not solve analytically in one coordinate system like the XYZ, the Cartesian coordinate system, but you can solve it if you make a clever transformation. And obviously, as we discussed in the beginning of the semester, if we make a transformational basis, we do not change the physics. I mean, the energy of the system should stay the same, right? So you will see many such things which are conserved, like probabilities are conserved. So you cannot find a smart change of probability, which makes you a lotto millionaire. Sadly, the probability has always to be the same to become a lotto millionaire. So the dream of the immediate luck is something which we have to struggle with for the rest of our lives. Somebody's lucky anyway and wins. Okay, let's take a look at the mathematics which we need to look at. And I'm going to switch over to the whiteboard for most of the rest of the time today. So let's do that. Sometimes this can be a little bit slow in coming up here. But now it should be here. So if we now look at the kind of overarching aims which we want to, is we want to start with a force. So I'm putting vectors here. It may depend on the absolute value of this parameter r. So this is my fancy way of writing the letter r. I hope you've gotten used to it. And this is given by the gradient of the potential. And then we have a potential which now depends only on the relative distance. And this quantity r, which we are going to look at, is the distance between 2 objects, which, if we now place ourselves in 3 dimensions, is going to be the, and we use a Cartesian system, then this is going to be given by this quantity here, c1 minus c2 squared. So this is a scalar quantity. And we know that if we look at the gravitational force, this is derived from a potential which looks like this. So we have the gravitational constant, and then they have the 2 masses, and this is divided by this quantity r, the relative distance. So remember now that these potentials, they are scalar quantities. They don't have any direction in space. But the force, since that's a gradient of the potential, that has obviously a direction in space. And we are going to rewrite this in a more compact way. We will often see this being rewritten like this, where gamma is a constant, which in our case includes the gravitational constant times the 2 masses. But in general, when you look at this, it means that what we are going to do now is not limited to the Coulomb force only, not to the gravitational force. This could actually be the Coulomb interaction, which also goes like 1 over r times some constants. Now, what we are going to see later, and this is more in connection with the midterm, is that you can put a power of k to this r, and you will still find that the energy is being conserved, angular momentum is going to be conserved, etc., etc. Except that you may not get a stable motion for, let's say, the solar system. And you're going to see that in the simulation. So if you change that r to the power of 2, you will get a solar system which is unstable. So the orbits won't be stable anymore. But energy will be conserved, angular momentum will be conserved, and all these other properties. But the orbits will not be stable with respect to the Earth moving around the sun, which means again that this is a kind of empirical observation which can be used to actually rule out other types of potential forms. But you will see that when you play around with the different powers of k in this relative distance r. So that's going to be one of the exercises in the coming midterm. So this is not limited. And the thing which we are going to do now is much of the same exercise as we have done before. So you will perhaps not be surprised to see that we are going to plot this potential. And the way we're going to plot this potential now, this is now plotted in as a function of r. So remember now that r takes values between 0 and infinity. So we have either transformed to polar coordinates or to spherical coordinates. So I'm plotting the potential as a function of r. And this needs some care, because if I just plot the potentials as you see it, it's not going to look like the way I plot it now. So I'm coming back to that. So what I'm going to plot is what we are going to call an effective potential. And I'm coming back to that. And it's going to look like this. We're going to have something like this. So this is the way the potential is going to look like. And it reminds you a little bit of that potential which you had in the last homework, the so-called Lennard-Jones potential. So many potentials in physics, they look like this. So there's an intermediate region where you get a negative potential, which means that we call this an attractive potential. And then you have a region where two objects are getting close to each other, where they repel each other. And then you have a region where it basically fades away. So the Coulomb interaction and the gravitational force, they have actually a infinite range, because one over r, the way it drops down when r becomes infinitely large, means that the potential actually ends up having an infinite range. So what we are going to look at now, and we are going to derive this in polar coordinates or spherical coordinates. So we are going to see the following. So if I now look at this point here at the bottom, and now in this case, kinetic energy is different from 0, and the potential energy is also different from 0. And the kind of motion which we are going to get here is circular motion. And we are going to see that many, many times. If I'm, on the other hand, suppose now I place myself in another position in this well. Suppose I place myself here, and I could now say that at this point, I have 0 kinetic energy. Now this object will then oscillate back and forth between these 2 points, as you saw in the first midterm, right? So much of the kind of insights which you got in the midterm are things which we're going to use now. Now that specific motion, since energy is conserved, so in both these cases, so this energy is conserved here. So let's put this as an E1, and then we take the other one, and then we call this an E0. This type of motion, which we're going to get now when it oscillates back and forth, is going to give another type of orbits. So if you're oscillating back and forth between 2 points, what kind of motion would you expect? So I said we had circular at the bottom, and we are going to show that from the mathematics. But if you now oscillate back and forth here, what would you expect as a kind of motion? Yeah? An elliptical orbit. So we're going to derive an elliptical orbit here. And the thing now is that the system is going to move between these 2 points, and it's never going to escape that elliptical orbit. So that means that if our Earth now moves between these 2 extreme points, so you see you have 2 radii. One is called these 2 radii, which are the distance between the Earth and the Sun, they have a name. So does anyone remember? Any aficionado of astronomy here? They have a specific name in astronomy. Yeah, aphelion and perihelion. We're on the right track. So that's these are the two distances, the shortest distance between the Earth and the Sun, and the longest distance between the Earth and the Sun. So you would then typically say that what you would see then is that this would be the largest distance between the Earth and the Sun, and the other one would be the shortest distance. And we are going to see that when we do the mathematics. This is actually the strength of what comes now, is that we will actually see from the solution of the equation that this is the case. That's pretty neat, actually. Then we have some other type of motion, and I'm going to place that one here. So suppose we are here now. Let's call this an E3. This is something which may not be intuitive. What kind of orbit may come out of that type of energy? But you see now that what happens is that since this energy is along the x-axis or the r-axis, you can actually go from 0 to infinity here. So that means that the object can go infinitely far away. So this is going to give us what's called a parabolic orbit. So this is a parabolic, and we are going to derive that one as well. So this is parabolic. And then we have the final one. So suppose now we have an energy here. Let's call this for E4. So this is the energy which we have. And I don't know, I actually didn't know the name, but it's actually a hyperbolic. So what it typically means is that for the circular motion and the elliptical motion, oh, I forgot to write that one, sorry. For the elliptical motion and the circular one, the object are going to move around another object, whereas for parabolic and hyperbolic, it is just going to escape away. So hyperbolic motion could be, for instance, a comet coming close to the Earth, and then it gets deflected, and then it disappears. And after some time, it is an infinite distance away from the Earth. So that would be an example of a hyperbolic type of motion. It has enough energy so that the potential, which means the attraction between the Earth and the comet, this potential is not strong enough to pull in the Earth. So it has more kinetic energy than potential energy. And kinetic energy wins, and then this comet just escapes, fortunately. It doesn't smash against it, yeah? So parabolic motion would be pretty close to the hyperbolic, except that your orbit would be more something which goes around like this. Whereas if you think of a hyperbolic one, we could draw it here. So suppose now that you have a, so let's say this is a good question actually. So let's try to draw it. And suppose now this is the Earth. So you could now think of an object which comes in. So this could be a comet. And depending on the energy, it could now move around like this. So either in circular or elliptical motion. And it would move in an orbit around the sun, now the Earth, like the moon is doing. So you could think of something coming in and close to the Earth, and it has an energy, a balance between kinetic and potential energy, which makes the Earth pull it in, and then it moves in a circular orbit. If you're thinking of a parabolic orbit, you could now think of an object which comes in here, and then it gets deflected like this. So this would be an example of a parabolic orbit. Now, a hyperbolic, on the other hand, would be more something like this. So you have the object coming in here. It looks very much like a parabolic, and then it goes out like this. So that would be the kind of very schematic way of understanding a parabolic and hyperbolic orbit, the way they get deflected by the object they're coming into. And we are going to see that when we write down the equations and solve the equations. So we can take this overarching look and just look at the potentials. And from that, we can infer something of the type of motion which we are going to see. So we are going to see that we conserve angular momentum, and we conserve also linear momentum, and we're going to conserve energy. So what we need now is a series of technicalities. So this is perhaps the least exciting topic. And some of these are actually in the homework, which we have, exercise 2. So this is homework 7, and this is exercise 2 here. So the first technicality we need, and now we're going to look at 2 objects. So we have n equal 2. So we need to define the center of mass of the system. So this is the central mass position. And we normally shorten this with an acronym, COM. And this is just the weighted distance between the 2 objects. So it's going to be an M1 plus an R1. So these are, if we now define an origin, this is now the mass center between these 2 objects with a given origin. And we have an M1 plus an M2, and we are simply going to rewrite this one as an M1 plus an M2 of an R2 divided by the total mass, where this M is equal to M1 plus an M2 here. This is the central mass, and then we define the relative distance. And we are going to transform from a Cartesian or from R1 to R2 to the relative and central mass coordinates. So we define the relative distance, which is this little r, which is R1 minus R2. So I hope you've gotten used to see my clumsy way of writing the letter R. So I apologize for that. This is one of these letters I always struggled with writing when I was a small kid, when you were forced to write letters in a specific way, and by some kind of odd thing, I was never able to do it properly. And this stays with me. Okay, sorry for that, guys. Then what we can do next is to redefine these R1s and R2s. So we can now use these 2 expressions. So we use this expression here, and we use this expression to rewrite R1 and R2 in terms of that. And you probably seen this expression here. And you can now rewrite R2 by manipulating the central mass and the relative distance. You can rewrite R2 as an R minus, and then you have M1 divided by mass multiplied with R. And then we have R1 is equal to R plus M2 divided by M times R. Have you done this exercise in Physics 181? Is that something which rings a bell? Should we take just a minute or 2 to go through the derivation? Or is it okay if we don't do it? What's the popular vote? So we don't do it. Okay, good. Maybe it's offensive to actually ask that question because you've probably seen the derivation here. Okay. Then next, what we define next is the total linear momentum. As I said, we just need to repeat many of the things which we have seen before. And we know that if we have n objects, this is given by the sum over the individual momenta, PHY, and we sum over all the objects which we have. And this is, if we assume now that the masses are time independent, we would have an MI, and then we have the derivative of Ri. This is just our velocity. And we know that since R is given by this expression which we have here, M1, times R1 plus M2 times R2 divided by the total mass. We can now, if we take the derivative of this quantity of dr, of not that one. Sorry. DOR dt, which I'm going to rewrite like this. We see now that this one is nothing but the expression which we have if we now multiply with m here. So I'm multiplying away m in the denominator in this expression here, in this one. And then you see that this is nothing but m, the sum over the mi's, and then I have a d of ri of dt, which again is the same as the sum over all the momenta of p of I, which again is equal, so this should be times m, which again is equal to m times r, like this. Now comes a very important result. And you remember now from the before spring break, we defined the net force. And now we're going to look only at internal forces. There is no external force in the system. So we know that this one is the same as the derivative of the total momentum, P derivative, the time derivative, which again is the same as m times the second derivative of the central mass position. So this is just a quick reminder of what we did before. Now, what happens with the internal forces if we have more than one object? What does that sum up to? Does anyone remember that? Yeah? Yes. So due to Newton's third law, the net forces, since we only have internal forces, is going to sum up to 0. What does that mean for the linear momentum of the total system? Yeah, it's being conserved. So this is actually extremely useful, because what it means is that the acceleration in the central mass coordinate is actually equal to 0. And this is going to allow us to simplify the problem, because we are going to get a similar equation for the relative motion. That's not going to be equal to 0, but the one for the central mass motion is going to be equal to 0. And remember now that if we have two objects, and we are in this is a 6-dimensional problem. 2 objects times 3 dimensions. That gives you 6 degrees of freedom. So if I then have an equation like this, where the acceleration is equal to 0, it means that I have reduced a complicated problem in 6 dimensions to one in 3 dimensions only. Because the equation, when the acceleration is 0, that is a trivial equation to solve, because we know that when we integrate it up, it's equal to a constant. So this is something which really helps a lot when we have this type of forces. So if we now just remind ourselves a little bit about the F net, so let me quickly say that. So F net, when we have only internal forces, is equal to this lovely number, 0. And we know that this is the sum over I, different from J, so this is a double sum. And then we have the forces Fij. And this is now, if we have only n equal to 2, then this is equal, F net is equal to F1 plus F21. And we know that this is equal to F12 minus F12, which is equal to 0, because F21, due to Newton's third law, is equal to minus F12. So this leads to a extremely useful results for us, and that is that m times the acceleration in the central mass coordinate is equal to 0. And this means also that the linear central mass momentum, the linear total momentum, which is the same as P, which is m times the velocity of the central mass motion is equal to a constant. So, as I said, if we have a problem now with the a typical problem like this, what that means is that solving the equation for the acceleration in the central mass coordinate is a trivial equation to solve. So what we need to focus on is actually the relative motion. So let's take a look at the relative motion now. So that's the next technicality which we need to look at. So the relative motion, if I now set up the acceleration, this is nothing but the second derivative of the relative coordinate, which we would rewrite in terms of the two dots here. And that has to be equal to the acceleration for the coordinate R1 and minus the second coordinate. So that's just taking the derivatives, the time derivatives, and using the definition. If we go back then, what this means obviously that the R12 is now given by the force F12 divided by M1. So this is now the acceleration for object 1, and it's under the influence of object 2. So there's a force between 1 and 2, and then there is a minus, and then I have an F21 divided by M2. Does that make sense? So now I know that F12 is the same as minus F21. So I can rewrite this second term here in the following way. So I have F12 here multiplied with 1 over M1 plus 1 over M2. And it's common to define, and you've probably seen this before, the reduced mass. And this is given by M1 and M2 divided by M1 plus M2, the total mass. So when I now sum up these two terms, I actually get the reduced mass. So what this means when I plug it in is that I have R is equal to F12 divided by this term mu, which in turn means that I have my other equation of motion, which says that I have R equal to F12 here. And if I then add the total mass times the second derivative of the central mass, these are the equations which we need to solve. Now, the last one, as we said, is trivial because it's equal to 0. And if you think of this as a problem in 3 dimensions, you have 6 degrees of freedom, x, y, z for particle object 1, and x, y, z for object 2, which means that in total, what we have, if we were to write this out in terms of x1, x2, y1, y2, etc., as we have done, we would have 6 differential equations. Now, in this case, we have 1, which is pretty simple. And since we have a vector over the central mass position, this means that we have 3 degrees of freedom. The x, y, and z values for the central mass with respect to an origin. And then we have the x, y, and z for the relative motion with respect to the same origin. So just keep in mind that what we have now is some kind of origin which we have defined. And you could now think of this in 3 dimensions. So we have our x, y, and z. We have an origin. It's not uncommon just to define this as our origin. And then we have the vectors R1, and we have R2 here. And then we have the relative motion here, which is given by R here. So what the next thing which we're going to do now, when we show that the angular momentum is conserved as well, that is going to reduce the equation for the relative motion from 3 degrees of freedom to 2 only, because angular momentum is conserved. And if you think of angular momentum as being perpendicular to the plane spanned by velocity and position, when that is constant, you could think of angular momentum pointing in the z direction, and being constant, nothing happens in the z direction. So we can neglect the z direction. And then we can only look at the x and the y directions. So we are going now to reduce that equation for the relative motion into an equation with only 2 degrees of freedom. And then we can use polar coordinates. So the whole trick then is to actually solve that equation in polar coordinates. So I hope you see, as I said in the beginning, the wood for the trees, because there are many small technicalities, but they all follow from the way the force looks like and conservation of energy, momentum, and angular momentum. So these things which we have seen again and again, they are coming to our rescue in order to simplify the equation we're going to deal with. Does that sound okay? Any questions so far? Things unclear? You've probably seen many of these things before, right? But we're just going to put them in the context of gravitational forces now. So the next thing we need is an additional ingredient, and now we need the expression for the force. So we need this F1, 2 here. And we know that this F12, so I'm going to be a little bit sloppy with notation now. I'm going to have to switch that over to F. And this is going to be a function of R. And this quantity here, we know that that one is given by the gradient of the potential. So in this particular case, we do have the potential, which only depends on the absolute value of the distance between two objects. And in our case, this potential, so this quantity which we have here, is just given by minus, and then I have my, if I stick with Cartesian coordinates, I have this quantity plus dy, and then I have the y with the y vector, and finally the unit vector in the z direction. And this is now multiplied with minus gamma divided by r, which again is x squared plus y squared plus c squared. So note one thing now, that I'm actually dealing with the x and the y and the z coordinates for the relative motion. I'm not setting in x1, x2, x3, and x4, because the potential depends only on the relative distance. So that means I don't need to take the derivatives with respect to x1, x2, because then I would find the force due to x1 and the force due to x2. But now the force depends only, or the potential depends only on the relative distance. And this is similar to what you did in the previous homework, in homework 6, when you took this Lennard-Jones potential, because you didn't need to take the derivative with respect to x1 and x2, and y1 and y2 and z1 and z2, but you simply needed to look at the relative distance. And we know how to take the derivatives here, but let me just quickly remind you of one of them. So if I take d dx of, and now I'm just looking at this term here, which is the only one which depends on x plus c squared. If I take the derivative, this gives me minus, and then I get x divided by x squared plus y squared plus c squared to the power of 3/2. And now I have a minus sign here, a minus sign here, so that gives me plus, but then I get an additional minus sign due to the derivative here, where I have 1 to the power of 1/2, 1 to the power of 1/2. And you see now, if I collect all these terms, what I'm going to get is that my force is going to be equal to this minus gamma, and then I'm going to have x times I plus y times j plus z times k divided by this quantity, which is now, I'm going to rewrite it in terms of r cubed. And this is again the same as minus gamma multiplied with r, the vector, divided by r cubed, which we often can rewrite in terms of the unit vector, which is 1 divided by r squared, and multiplied with the unit vector, which, as we know, is given by r divided by the absolute value of r. So when I've been writing r so many times, it has to end up with some strange forms here, like the last one. Just imagine that is my attempt to write a letter r. Sorry for ranting about this. I hope you see that from the context. Okay, so this is the force which we have. And when we go back then, what we have is mu times r. And this is going to be given by this constant minus gamma divided by, I'm going to use this r cubed multiplied with the vector r. So that's the equation which we need to solve now. And that equation is an equation which has an analytical solution. And if I divide, if we now look at this constant gamma is just g times m1 times m2 here. And I know that mu is given by m1 times m2 divided by the total mass. So if I use that one, then what I see now is that I get r, which is the acceleration in the relative, for the relative motion. This is going to be given by minus g multiplied with the total mass, multiplied with r, and divided by r cubed here. Okay, so what we need next now is to make a change to another coordinate system. So we can, and you are going to encounter this in many, many physics applications, we can use something which is called the center of mass frame. So remember now that we can always rotate ourselves and redefine the positions. So what you could do now is to say that the center of mass position is equal to 0. And that's a very common choice because that simplifies life a lot. And you will see that then the equations simplify further. So this is just a choice. It doesn't change the physics, but it's just you changing the reference frame. Have you encountered this before? So this is a central mass frame. And if we do that, we can simplify the equations. So that's the next technicality. So this is the C of M frame. And in that case, we simply set R equal to 0, which means again that we now have a slightly different picture now. So we have an R1, which becomes simply equal to M2 times the relative coordinate divided by M. And we have R2, which is simply minus M1 times R divided by M. What this means also is now that if we look at the system we have, we would have something like this. So this is R1, and then we would have R2 pointing this way. And we have here the central mass where we are equal to 0. And then we're going to have a velocity which goes this way, V2. And then we're going to have a velocity V1 here, as we're going to see pretty soon. The total angular momentum is obviously now given in terms of the two angular momenta. And if we just remind ourselves that P of I, so this is the momentum of each single object, M of I times Ri, then we can set up the total angular momentum, which is a quantity we are going to show now is conserved, following much of the same arguments which we used before spring break. So we have L, is the total angular momentum, is simply going to be R1 and cross product with P1, so this is that one, and then we have the next one, which is multiplied with P2, which again means that if we now take the masses here, we have M1, and then we get R1 multiplied with R1 derivative, time derivative, plus M2 times R2 here, crossed with R2 derivative. And now we can insert R1, which is equal to M2 times R divided by M. And then we do the same with R2 here, which is M1 times R divided by M. So we would place these two guys, this one in here, and then we do the same with that one in here. And we can also use the fact that the derivative has to be equal to, of R2 has to, time derivative of R2 is proportional with the time derivative of the relative motion. So if I plug in these terms, both for the time derivative and for the vector itself, what we will get then is something which looks like this, and I leave this as a small exercise to you guys so that we can actually, this is actually part of the exercise, exercise 2 in the next homework. But what you can show then is that this can be rewritten in terms of the relative mass, and then I have the position, the relative coordinate, times the derivative of the relative coordinate. So this is part of the exercise 2 in the next homework. Now, the next and final step today is to show that the angular momentum is conserved, as we did earlier, except that earlier we took it as a function of just one variable. Now we're going to look at the relative position, which is the distance between R1 and R2. But we can show now that the dl dt is going to be equal to 0. And what we do now is simply to repeat what we did before spring break. So we know that this is equal to mu, and then we get the d of r dt times, and this is actually dr dt, plus mu multiplied with r and dotted with d of r second derivative of dt. So if you look at the first term, do you remember what that should look like? So if you take the cross product of a vector with itself, 0, exactly. So that should be 0. So the first term is something we don't need to think of, and that is equal to 0. Because it's just two vectors which are equal. And then what we get then is simply mu of r times r second derivative. And this we know is equal to the force, mu times r second derivative. So this is the same as r multiplied with this force which we have. Now comes the next thing, and we know that the force which we are looking at is given by minus gamma divided by a scalar quantity, r, there's no vector here, and then multiplied with r vector. So that's the force which we're dealing with. So if I plug in that one, what should I get then again? 0. Excellent. So this is also 0. So that means that both these terms are 0. So, and this is again equal to 0. So that means that dl dt is conserved. L is a constant. And this is roughly as far as we get today. And these are the technicalities which we need in order to pave the ground for solving the differential equation. So what happens now is that you know that R and the momentum, they span a space when you take the cross product. And since the angular momentum now is perpendicular to that plane and it's conserved, we don't need to think of any changes in that direction. So we could think of R and P, the momentum, being in the XY space, and that Z defines the axis where the angular momentum lives. And since that's a constant, we don't need to deal with that degree of freedom. So we can reduce the problem now to simply XY as degrees of freedom. And then we're going to transform it on Wednesday to polar coordinates. And we will see that we can solve the equations analytically. And we are going to get elliptical orbits depending on the energy. So that's pretty neat. This is one of the few cases where we have analytical equations. And if you think of historically, this is something which dates back to Newton, Kepler. Just Kepler, when Kepler cooked up the laws, Kepler had only observational data from the 15th and 16th century, which is pretty amazing. Okay, guys. This topic is pretty cool. I love it. And I hope I can transmit some of my love for this topic here. It's fun. Okay, I'm going to switch up the recording. But if you have questions about the exercises, feel free to hang around. Yes.